what did you came up with your answer? Is using interrupt always good? Is interrupts are the ultimate solution to all our problems? Or are there any further problems with interrupt as well? Again, adopting from generic common sense, most of the solutions that we come up with are just a solution that seems good at that time for that problem or might be working at that time, but it might not be the ultimate best solution. There might be some problem even with our solution and it needs to be further refined or improved, right? I think most of you could relate with some of the other situations in your life with what I just said. Coming back from philosophical discussion to our technical discussion, is using interrupt always good? No, in one word answer. Why no? Well, think of a scenario if the device is fast to mostly complete its tasks by the first pole. So in such a scenario where device is really fast and even by the time, like every time by the time of first poll itself, the device has already done the task that it's supposed to do. So coming back to this diagram, here we have 3 seconds as a stall cycle, but let's say this disk is really fast. And even by the time of the first poll, the device is already done. So after the fourth cycle, CPU issued the task to the disk. And at the fifth cycle, when CPU polls, the disk already has the data right there, completed. So then basically there are no stall cycles in that case, right? If disk is that fast enough, complete its task between fourth and fifth cycle. So even before the first poll, the data is ready. So in that case, now if we use interrupt, what are we losing? If we use interrupts for such a fast device, then we have this overhead of switching to another process. Because, well, CPU needs to, in case of where we are processing with interrupt, CPU needs to think of what other task it's still remaining to be done. So for example, task number 2, so it needs to switch to that task number 2. So there's some overhead of switching to that task, contact switching overhead. Then we have second, we have overhead of handling the interrupt, right? We need to set an interrupt, excuse me, set an interrupt and raise an interrupt. So that overhead of handling the interrupt, and we have overhead of switching back to issuing process. Because we know that once the device is done, then the CPU returns back to that process. So if the disk is very fast, what would happen in case of interrupt is we don't have 3 seconds for the device to that the device takes, but the device is too fast that it returns right here at this time. But meanwhile, if we are using interrupt, then we need some time for the CPU to go out and look for the other task. such as process 2 that it fetches over here. So we loses that time. Maybe CPU might still be finding another process. So CPU might still be contact switching. In that time itself, the device returns somewhere in between. So we have wasted that additional time after we already have the data, but the CPU is contact switching. Then definitely we wasted some time to set an interrupt, and once the device is done, device would raise an interrupt. So that is also some additional latencies. And once the device raises an interrupt, then CPU have to contact switch back again from process 2 to process 1. So that's again an additional latency. So all this for nothing. If we would have just stick with polling, then we wouldn't have any of these overhead, right? So interrupt is not the solution to all the problems in the world, but it has its own challenges. It could be expensive for the devices that are fast and the devices that that can respond back even before the time of the first polling instance, or maybe a couple of polling instances, because we don't know what is the time that it takes depending on processors efficiency. How much time does it take to contact switch? How much time does it take for the hardware to set and raise the interrupt? Depending on all these latencies, maybe polling for a couple of cycles is always much efficient than going with all this additional task in the process of contact switching or in the process of interrupts. There is one more problem, and I hope some of you have already thought of these problems. That's what made those lectures interesting and exciting, to stick together and compete with the process of your own thoughts. Of whenever I raise a question, you would have thought of some prospective answers, and if that answers gets right, that's the problem that we discuss next. That means, yay, you've won it to yourself. So there is one more problem. What is it? The problem of too many interrupts. And too many interrupts could cause the problem of live locks. What do you mean by live locks? If you have never heard that term, is the process, basically process 1 or process 2, any CPU process, what it is doing is only processing interrupts. So imagine if there are too many processes. So if you have too many students in your class, back to our monitoring the class analogy, not 50, but imagine you have 50,000 students in your class, and imagine you're the only TA in that class. It would be the worst place to be, first of all. So now if you're using this process of interrupts, which is asking people to raise hand, you go to them to go to their desk and address their problem. And because there are just too many students, you don't have time in between where one student raise hand, you walk to them, you solve their problem, then you go look around again, another student raises hand, then you walk to them, you solve their problem. You don't have that time to either just solve the student's problem or to walk to them. That's basically doing the constructive work. When you are solving the student's problem, you're doing constructive work. Otherwise, when you're just looking at interrupts or walking from one interrupt to the other interrupt, that's all wasteful work, right? You're not doing anything useful. You're just processing interrupt. Or while student is the time that student spends in raising the hand, that's again just a wasteful time. Maybe a very less microseconds, but still a wasteful time. So imagine a live lock where you are not doing any constructive work, but just spending all your time in just processing interrupts. So basically wasting all your time. That happens if there are too many interrupts. So if there are too many processes and all these processes are waiting on so many tasks or raising so many interrupts, the CPU would basically spend all its time just processing interrupts, raising, setting hardware interrupt or raising interrupt or context switching from one process to the other process. And it wouldn't get time at all to do any constructive work. So that's again a big problem. Now that we know the pros and cons of polling, why do we need it? We know pros and cons of interrupt, why do we need it? Where can it be helpful? What are the caveats where interrupt is not a good solution? Then what do you think would be a better solution? Knowing the concepts of polling and interrupt, can you come up with an idea of how we would solve this problem in a better way? Well, one thing that's tinkling in my mind is to use hybrid, right? If you have technique one, which is not the best, but could be good in some scenarios, technique two, which is not again the best, but could be good in some other scenarios, then why not take best of both these worlds? So why not generate an hybrid technique, which would poll for some time. So it would wait for some cycle if the device is fast enough, right? If the device is fast enough, then polling is good. So it would poll for some time. If the device is fast enough, it would return and then we could continue our task. But if the device is not fast enough, then interrupts are good. So it would poll for some time and then use interrupt. That is one smarter way to take advantage of both this process of polling and interrupts and to come up with a solution, cost-effective solution. And another solution, do you need some more time to think? And another solution is coalescing. So coalescing is what? Process multiple interrupts in a group by waiting for some time for accumulation. So as we saw, the major overheads of interrupt is setting an interrupt, raising an interrupt, and contact switching. Now, if we use the technique of coalescing, then we are waiting for multiple tasks or multiple interrupts in a group to complete the task at once. So basically, we would be waiting for multiple processes or multiple devices to either once they are done with their task, we wouldn't raise an interrupt right there. We would wait for a while after the disk is done with its task, hoping that even in the same time, in the meanwhile, there are other disks, even they would be done with their tasks, right? And once we have this bunch of disks that are done with the task, then we would raise an interrupt. So then CPU, which was working on another process, would then come back to this to resolve this interrupt. So such a process of coalescing multiple interrupts in a group by waiting for some time for accumulation can help us to reduce that multiple contact switch overhead where CPU have to come back. just goes and then another interrupt is raised. So it again have to come back. So neither it's able to make some progress over here, nor it's able to make some progress over there, but rather it's just wasting time in switching from here to there. And the worst case of wasting all the time in switching is a live lock, which we just discussed. So such a smart trick of coalescing or combining multiple interrupts together would be able to resolve the live lock. Thinking this again in the practical scenario where you have multiple students in your class, coalescing is something like asking people, okay, once you hear to the question of one student, saying it loud, okay, everybody who have this question, listen to me. This is how you solve it, right? That's how you're coalescing multiple interrupts and resolving them, taking care of them at once. And then you may be able to take a class of 50,000 students if you apply these techniques. That concludes our discussion on what are the different components in storage system stack, how these components interact with each other. We saw with a very basic example of how we have the device, a very simplistic version of device, and a few, just 3 resistors in that device, how that would operate. Then we saw some problems while operating with that device, problems of, and we saw how to tackle that problems by polling and by interrupts.